현석 씨, 받을까요? Check. Okay, let's start the 10th class meeting. So in the last class meeting, we started to study this paper entitled An Optimal Orthogonal Overlay for a Cyclostationary Legacy Signal. And I explained the title, why we talk about orthogonality, that is a geometrical concept. And I also explained what is the notion of overlay and what is the meaning of legacy signal. So legacy is kind of owner or pre-owner of the spectrum. And here, overlay system is a new system that is going to utilize the spectrum together with the legacy system. And orthogonality is geometrical meaning, but we have two meaning. First, at the oversampling receiver, we have zero interference, but still it does not justify why we have this geometrical concept. And I briefly showed you the converted formulated problem where we have this line, which can be interpreted as a vector-vector multiplication as this vector inner producted with the transmit waveforms vectorized Fourier transform equals 0 for all f in the Nyquist zone named calligraphic letter F, and also it must hold for all k and for all else sample. Got it? So this was the name of the title. And I also explained the important different notions of transmit band and receive band and channel band. And the channel band is, interestingly, can incorporate some spectrum nulling condition by setting some frequency subband to 0. Got it? And that is a very interesting trick you can avoid, with which you can avoid variable length vectorized Fourier transform or two-dimensional power spectral density matrix. Got it? Today, we are going to delve on more on this problem. But before, I'm going to give you some intuition how this kind of overlay is possible. So let's think about very special cases where our intuition really works. Suppose in the time domain, you have a stream where a QAM symbol, QAM modulation symbol is multiplied to a rectangular pulse. So suppose this is S of t, or if you want, this is a filtered version of S of t. So let's assume this as in our paper, S of t convert with H of t. Sorry, not this one. I am sorry, SKHK. So K is a signal. Got it? So let me see and check what kind of notation did I use. Okay. Legacy. Okay, where is the legacy signal? Where is the legacy signal? Okay. Yeah, there is no legacy signal. Okay, so that's why I got confused. So let's forget about this legacy signal concept and just consider a signal, let's say A of t, that is multiplied by the, no, this is not good. Okay. So suppose you have a signal, S of signal with rectangular pulse with t, and you have uniform delay, and you have some nth symbol. Here, positive and negative infinity means very large number of symbols. It shouldn't be interpreted as real mathematical infinity. This is just a model. So if it is 1 and negative 1 and 1 and 1, then you will see some waveform like that, right? Now, suppose this is the legacy signal, and you want to design your overlay systems signal so that you have perfect orthogonality to this one. If there is no bandwidth limitation, what would be a good choice? The first one is that you somehow find the timing of the legacy signal. So let's say that this choice of time origin 0 is carefully chosen by estimating the transition of two pulses. And you also want to align your signal so that you can transmit, for example, QAM symbol with some waveform. What can you do? The simplest approach would be you have some orthogonal pulse, orthogonal to this rectangular pulse. And it could be 1, 0, or 1, negative 1. Now you multiply your own signal. Then you may have perfect orthogonality, right? So this pulse is orthogonal to that pulse. And if you have negative 1, then you have this one. Again, positive 1, positive 1. Then these two signals, whatever symbol A sub n, B sub n you have, they are orthogonal, right? And in this time period, whatever symbol A n, B n you have, they are orthogonal. So you know it's possible. This problem is not an impossible problem. Got it? Now, in the time domain, it can be easily understood. But what about in the frequency domain? Since we are employing a rectangular pulse in this simplified example, and if we assume A sub n is uncorrelated data symbols of zero mean, then our power spectral density of the legacy signal is sinc squared. So you have this zero touching points are all integer multiples of the inverse of the symbol period, except at the origin, right? Probably you remember this sinc square pulse from the OFDM, right? What about the overlay signal? What would be that? This pulse give you sync pulse. That pulse will give you delayed sync pulse. So actually, these two signals combined as a single pulse is what? In the frequency domain. First, this rectangular pulse is narrower, half narrower than the above one. So if you just look at this spectrum, not the power spectral density, but the Fourier transform, you have sync pulse with wider bandwidth because in the time domain, it is shorter. Now, if this is sync sync F. Proportional to sync Ft, then this part would be proportional to sync 2Ft. Yeah. 1 over. Yeah. So this one will give you narrower sync. However, you have that part, which is in the time domain, delayed version by T over 2, and flipped. So in the frequency domain, what happens? It is sync 2Ft times, am I right? Yeah, 2Ft times 1 minus e to the positive j 2 pi f capital T over T. Got it? And what is this one? Using the Euler's identity. So what you can do is that you can factor pi ft e to the negative j pi ft minus j pi ft negative. Am I right? No, plus. Yeah. I believe I'm correct, right? So what is this one? Again, if you divide by 2 and multiply 2, this will give you sine, right? Due to the Euler's identity. And if you put j and j here, sine what? This angle. So the Fourier transform of this pulse is what? Sync 2ft times sine 2 pi ft and some constant 2j, so it's proportional to that. The reason why I do not think about the exact proportionality coefficient is that anyway, we are going to scale it and scale because we don't know the power. And what do you have? The power spectral density is sync squared 2ft and sine squared pi ft over 2. Got it? And what is this one, by the way? This one looks like something like this, right? If you have a sine pulse squared, then it's raised and negative cosine, right? So you multiply these two, then you have something like, I do not exactly remember, but here it looks like that, and it occupies more bandwidth, sometimes like that. So in this example, the simplest orthogonal overlay, assuming that at the receiver, the legacy receiver uses the matched filter matched to this pulse, and the overlay system is matched to this pulse, and legacy system has that pulse, and it samples at this rate without oversampling because two signals have the same symbol time. In that case, they have orthogonality, perfect zero interference to each other, right? Because this signal is orthogonal, that signal is orthogonal to each other. So you know that in some special cases, this problem makes sense at the cost of what? At the cost of larger bandwidth of the overlay system than the legacy system. Got it? Now, what about the other way? Suppose overlay system has narrower band and legacy system has larger band. What kind of example you can imagine? So now, in the time domain, suppose we have some rectangular pulse-shaped palm signal, especially BPSK in this case, just for convenience. And you want to design some signal for legacy system that has narrower bandwidth, but orthogonal to this signal. Can you do that? Is it possible? And that question is not that simple, because even if we just switch the situation and use narrower band rectangular pulse, what happens? For example, within this 2t period, if the symbols cancel each other, then you have orthogonality. But if symbols does not cancel each other, you have interference, right? So it seems that designing such system may not be that easy. So slowing down, see that? The legacy system transmits slowly, right? Slowing down the symbol transmission rate, but still maintains orthogonality, looks not that straightforward. And we have no idea how to do that. And even we do not know whether it's possible or not. Do you have me? So it's not that straightforward. Our orthogonality must be deterministic, not statistical, right? On average, they are orthogonal. That is not allowed here. Got it? Actually, the paper solves this problem by slowing down the symbol transmission rate of the legacy signal. But here goes the trick. The bandwidth of this signal is not narrowed. In most of the cases, the perfect orthogonality is possible only when we use very wide bandwidth signal for each pulse. Got it? So this example, seemingly providing impossibility proof, not proof, but impossibility of such a design is right in the sense that narrower band signal may not maintain orthogonality, but it's possible to have wider band signal. How? For example, the idea is almost the same. Consider this example. So even though the transmission rate is reduced, you have such a pulse. Then what happens? Whatever symbol you have for this one, it cancels with that one whatever symbol you have, just consider BPSK or something, this signal cancels that one, right? So this signal, even with uncertainty in these symbols, can maintain the orthogonality. Got it? So that's the trick of this paper. And another one is this one. Here, we just consider orthogonality in terms of integration of that pulse with this entire signal from 0 to t. That is one thing. And from t to 2t, that is another. But in this problem, we may oversample for this first capital T period. So we sample half in the middle and half capital T, 3t over 2, 2t, something like that. Got it? So we have now vague idea. It might be possible under certain conditions. And we are going to mathematically rigorize, make it bigger, why this is possible, and when it is possible. Got it? And we are going to use geometrical interpretation. Now, let's go back to our previous example. Last time, I didn't talk much about this spectrum of the legacy signal and overlay signal. And interesting thing is this one. If I remember correctly, these two subfigures are for the same situation. But as I mentioned last time, here in subplot B, we considered 1, 2, 3, 4 different choices of our legacy system, given the overlay system, given the legacy system. So legacy system has capital T for the symbol transmission rate, and the overlay system chooses the same symbol period, half, 1/4, 1/8. So the overlay system slows down. Interesting part is this one. In these 4 cases, all 4 cases, the overlay system has the same power spectral density if the power is normalized. So this part, the PSD, is the same for all 4 cases. Got it? So just using the power spectral density, because power spectral densities are identical for different cases, does not give you enough information. Even you do not know what kind of symbol transmission rate the legacy, the overlay signal or system employs. And it's kind of obvious because as we've seen already, in cyclostationary signal, actually power spectral density is what? Just consider bispectrum. That is the double Fourier transform of the autocorrelation function of a cyclostationary random process. Then what happens? Let's consider 2 frequency axes. Then you have the kind of main diagonal impulse fence and off-diagonal impulse fences, right? What is the ordinary power spectral density here? Definitely this one must contain more information than the ordinary power spectral density. And the ordinary power spectral density is the height of the main diagonal impulse fence. So it's like this main diagonal impulse fence is nothing but this function, the product of the ordinary power spectral density of this Ysen cyclostation random process times delta of xi1 minus xi2, so that you have impulse fence and its height is the power spectral density. Got it? And now let's consider these 4 different cases. Then what is the same for these 4 different overlay system design? And what are the commonalities and differences of these 4 system designs? So you can easily see that these 4 cases, as far as the power spectral densities are the same, have the same this main diagonal impulse fence, right? Then what would be different? By the way, let me draw a little bit skewed view. So if we assume that the height of power spectral density, actually that is not possible because usually this bispectrum is complex valued. But here only the main diagonal has non-negative real valued, as we know, right? Because this power spectral density is always non-negative by definition, right? Limit of expectation of energy spectrum divided by time period, right? So this one is real valued impulse fence, but the other impulse fences may have complex valued height. So it's not that easy to draw, but we can say something. Suppose this is 1 over T0, and this is negative 1 over T0. And according to this figure, we have around 0.5 and 0.6 something, 0.5, 0.6 something. So we draw a line. Something's not correct, but anyway, so 5, 6. Yeah. Got it? Because if this is 1 over 2T0, then you have this thing. Am I correct? Yeah, I believe so. So here, from here to there, you have something like this. And from here to there, you have something like this. If you have this axis is some z-axis that comes from this surface. Got it? So you have the same main diagonal impulse fence. Do you understand this one? Do you see the 3-dimensional something here? Got it? So these 4 examples, if their powers are normalized, then have the same main diagonal component, main diagonal impulse fence. Now, let me ask you a question. What would be the major difference if you plot the bispectrum of the first, second, third, fourth cases? So in the first case, your overlay system has the same transmission rate as the legacy system. So here T sub 0 is the symbol period of legacy system. So your first design has what? Off-diagonal impulse fences that are 1 over T0 spaced, as shown here. Got it? And you may have some here non-zero impulse fence height on these two lines. Got it? Because the signal is band limited, we can never have non-zero impulse fence outside this square. And we have three lines. This line, that one, that one. So here, we may have some complex valued impulse fence cut off by these dashed lines. And over here, we have another impulse, complex valued impulse fence there. Got it? So that is the bispectrum of the first design. Now, what is the second design case? Now, we have what? The transmission rate reduced. Transmission rate is reduced, which means that cycle period of the overlay signal is doubled. And in the frequency domain, we have smaller value for 1 over t. So actually, what we will see is this. We will have one more impulse fence between these two. Because this length is 1 over 4t0. And that is half of the symbol transmission rate of the second design of the overlay signal. Got it? So now, what is possible? Here, on this line segment, you may have some non-zero spectral correlation. And also here, you may have some non-zero spectral correlation. And also here and there. So overall, you have 5 impulse fences that possibly have non-zero spectral correlation inside this legacy signal. And as you know, if we vectorize this one, what will happen? If we vectorize the first design, then we may have 3 outputs from our vectorized Fourier transform. 3 jointly Wise-and stationary random processes. If we represent our new signal, new overlay signal, as harmonic series representation. What about the second design? In that case, we have 5 branches in our vectorized, fresh vectorizer. And our modulators have narrower spacing in the frequency. Our ideal band limiting filter also has reduced bandwidth. That's why we have length 5 outputs, length 5 output vector from the frequency shift vectorizer. Of course, you may choose 3 output, length 3 vectorized Fourier transform, but in that case, your 3 outputs are not jointly Wise and stationary. Still, they are jointly cyclostationary. If you have perfect match in your fresh vectorizer, then you can transform the cyclostationary random process to jointly Wise and stationary random processes. By the way, for the first design, you can also use 5 output fresh vectorizer. In that case, what will happen? You still have 5 jointly Wise and stationary random processes. However, that's redundant because you have here 0 spectral correlation. But mathematically speaking, that is okay, right? That is still okay. Losing some information, such as spectral correlation, causes performance degradation in our receiver. Some redundancy, if optimally processed, does not lose any information. Remember this. Right? Now, what about the third and fourth examples? And since you are not just a dummy, you have a sharp-brained graduate students. Now, whenever you have 1 and 2, then many is obvious. So in that case, you have more impulse fancies possible for your design. So you may have better spectral correlation. And in this case, you may have more dense impulse fancies. Then you may wonder, hey, then just using very, very, very slow transmission looks okay. But actually, that is not true. The problem is this. We are only thinking about the overlay signal here. What about the legacy signal? And that is very slowly seen. Then the problem is this one. It's kind of obvious. If you compute the two-dimensional power spectral density, that is the power spectral matrix valued power spectral density of the fresh vectorized output, then when you use 3 fresh vectorizer, that is matched to the 1 over T0 for the spectral spacing, then you have rank 1 signal for the legacy. But if you double, then legacy signal actually is viewed as 2 signals, which means rank 2 signals. You will see outer product, which is rank 1, 2 outer products. And if you choose this one, you will see the legacy signal occupies 4 dimensions. And in this case, legacy signal occupies 8 dimensions. So just the slowing down to have more freedom actually counteracts with increasing number of legacy signals. That's why some of my graduate students already know that whenever in 통신신호연구회 project, they propose how to identify how many signals do we have, I always say that it's impossible mathematically. Even a single linearly modulated signal can be viewed, mathematically speaking, as 2 signals, 4 signals, 8 signals, any number of signals possible. How? Just take a look at this one. Suppose I construct one stream, signal stream, taking the even numbered symbols. Then you have what? You have symbol period 2t QAM signal. Now you take the odd numbered symbols, then you have another symbol period 2 capital T0 QAM signal. If you choose, even in this case, 3, then you have 3 signals. 4, you have 4 signals. So how can you, theoretically speaking, mathematically speaking, know that there is some signal? Of course, we may claim that that signal and that signal are the same, assuming only the delayed version of the first one, assuming that the channel does not vary very fast. However, for example, in spread spectrum system, direct sequence spread spectrum, every symbol pulse actually are almost pseudo-random waveforms. So we have time-varying pulses. Then how can we identify? There is only one. And some of my graduate students already know that. Suppose we have a QAM modulation symbol employed signal that can be decomposed using natural binary coding for many, many numbers of pi over 2 BPSK signals. And also, when we construct some strange QAM signal, we may use different pulses for different pi over 2 streams. Of course, it's not necessary, but suppose you are a designer for military communication system. Why don't you do that? It can confuse a lot of naively designed eavesdropping system. Got it? Anyway, so you will see what's the difference and what's not the difference. Anyway, so even before we start to delve on the optimization problem, we have some interesting idea. Now, so you may now say that, hey, then what's the difference of these 4 signals? Still, the first one has what? Rank 1 interference and my desired signal as an overlay system. Rank 2 interference, rank 3 interference, rank 4 interference. If I double the signal space, then number of interference doubles. So it appears that I have only limited subspace where I can put my signal. Is it true? It is true if we don't have any excess bandwidth. So here comes the important notion of excess bandwidth. By the way, if I just say verbally excess bandwidth, since I'm not the European or American native, my pronunciation is not correct. What I mean is this excess, not that excess. Okay? So this is the noun for excessive. Got it? So you know that suppose we have this form, single pulse uniformly delayed linear modulation, then what is so-called the condition for zero inter-symbol interference? As you know, Nyquist criterion. And Nyquist criterion says that as far as the bandwidth of P of t is greater than or equal to 1 over 2t. We are assuming complex valued signal. Then what? Can be a Nyquist pulse. By the way, what is the Nyquist pulse? That satisfies Nyquist zero inter-symbol interference condition. Got it? So whenever you have transmission period capital T, its inverse divided by into half serves as a fundamental lower bound for the design of zero inter-symbol interference pulse. So what happens? In the frequency domain, you have this so-called Nyquist zone from negative 1 over 2t to positive 1 over 2t of length 1 over t, right? 1 over symbol period. And if your P of f, the Fourier transform of the pulse, has some energy occupying more than or equal to this bandwidth, not less than that one like this one. So this kind of signal occupying less bandwidth than 1/2t, then you cannot avoid ISI. However, if you are allowed to occupy more than that, it's possible to satisfy Nyquist condition. And here, the trick is this one. Given the symbol transmission rate of the legacy system, this is the Nyquist zone. Actually, as you see here, here goes the trick. The legacy system has positive excess bandwidth. Here, positive and negative is determined this way. If the bandwidth is greater than 1/2t, then we are going to say that it occupies more than required. So what we do is that we divide bandwidth by the minimum required bandwidth. And what? If they are equal, this value is 1. So we subtract 1. And we call this one as sometimes alpha, sometimes beta, sometimes gamma. So let me use beta. Okay? Then what do we have? 1 plus beta divided by 2t equals b. Now let's see. If beta equals 0, what does that mean? Bandwidth equals 1/2t. If beta is greater than 0, the bandwidth is greater than 1/2t. If beta equals 1, what is that? B equals capital T, which is twice the minimum required bandwidth. So if beta equals 1, means twice the minimum required bandwidth is used in pulse shaping. And if beta is 0, then we are kind of critically utilizing the bandwidth. If beta is negative, then what? We cannot avoid ISI. Now, let's go back and see this example. Here, our legacy signal possibly transmitting square root raised cosine pulsed linearly digitally modulated signal has what? Positive excess bandwidth. And this positive excess bandwidth is probably around 22%. By the way, this value times 100 implies some, for example, 22%. Means that beta equals 0.22. And use of positive excess bandwidth is somehow necessary. One of the mathematical reasons is that if you set beta equals 0, there is only one pulse possible. Actually, not exactly one pulse, but its energy spectrum must be rectangular pulse in the frequency domain. And if we naively take the square root, of course, we can multiply some complex, strange phase rotation at each point and generate uncountably infinite different number of Nyquist pulses, but let's don't do that. In that case, sync pulse is the only pulse that satisfies beta equals 0 and Nyquist condition. And sync pulse, as you remember, sync pulse is what? Sine pi ft divided by ft, something like that. So as a function of f, function of t, what happens? Its numerator is bounded by 1, and its denominator is proportional to t. What does that mean? You use sync pulse for your modulation waveform, and if you add up symbol multiplied signal to construct mathematically defined QAM signal with infinite symbol waveforms, you don't have absolute convergence for the sample path. That's not good. Okay? So as you know that harmonic series, not harmonic series representation, but harmonic series in theory of sequences, what is that? 1 plus 1/2 plus 1/3 plus 1/4. And as you learned in high school math or calculus, that sequence partially summed up and plotted. It seems it converges to some value. However, you can prove that the sequence does not converge. Even though it's very slowly increasing, it blows up. What does that mean? If we use sync pulse, mathematically speaking, we cannot guarantee that each sample path of the signal can be well defined or not. So precisely speaking, mathematically, you shouldn't use sync pulse in representing the signal. An interesting thing is this is similar to, I forgot the name, somebody's horn. So you use 1/x, and it looks like a horn, some Gabriel's, some horn, I don't remember. That horn obtained by rotating this curve with respect to the x-axis. Interesting thing is that its surface is infinity, but its volume is finite. Why? Because 1/t, if you 1/t or something, if I remember correctly, then is it? No, 1/t. Yeah, so you have infinite surface. But if you square it, then integrate, then you have finite volume, something like that. And anyway, similar thing happens. So if you have sync pulse, signal power may be finite, but your sample path may not have convergence. Anyway, that is one reason. And another one is that anyway, we can never implement this continuous spectrum signal, right? We have continuity in our implementation. So anyway, we cannot implement sync pulse. Then what is the actually misleading design guide? Let's use positive excess bandwidth. By the way, I found that negative excess bandwidth is okay in other research, which paper is not included in our reading list. But for example, the so-called faster than Nyquist transmission, where we can use still well-defined square root raised cosine pulse, but transmit that pulse faster than its designated transmission rate for 0 ISI. Actually, that does not make any convergence issue, and it obviously induces non-zero intersymbol interference. But as you know from the information theory, having intersymbol interference is information theoretically is okay, as far as you have a very optimal decoder. You can remove the intersymbol interference, apparent intersymbol interference. Intersymbol interference in the code word symbols, not intersymbol interference in information symbols. So it's okay. But anyway, that is one of the myths. So let's follow the myth and use positive excess bandwidth as we have here. So we have 22% square root raised cosine pulse. So we have actually more than one dimension. We have 1.22 dimension. Got it? And this is interesting thing. So actually, this orthogonal design is possible by utilizing that 22% excess bandwidth. And you will see later that if you sample here and here, then you have a matrix that is multiplied by the desired signal's rank 1 matrix, it becomes 0 for all f. In that way, the overlay signal does not interfere to the legacy signal. Now, what if we slow down? As I told you, actually, the dimension for the first case is 1.22. And here, what is the dimension of legacy? 1. So we have 0.22 excess dimension which we can utilize or exploit. Now, what about the second case? Actually, you multiply 2. So now you have bigger dimension left by subtracting the original dimension by the dimension of the dimension occupied by the legacy signal. Of course, what is the trade-off? You slowed down your transmission rate, right? Now, what happens in the third case? You multiply 4. Now you have what? 88.88888 dimension you can utilize. And you may say that, hey, they are the same anyway if you properly divide. Here, the fourth case give you what? 어떻게 돼요? 2배 하면 어떻게 돼요? 9. 맞아요? 7. Okay. And this is what? 8. And you have 1.76. Am I right? And here comes something very interesting. Now, at this rate, your dimension is greater than 1. What does that mean? Now, you may design legacy system, overlay system that has 0 intersymbol interference for itself, because the remaining dimension is greater than 1. So relatively speaking, now the bandwidth the overlay system can utilize is greater than the Nyquist rate at this rate. That's why we have this strange phenomenon. See that? The forced design has what? Forced design has what? Has 0 ISI. First, second, third system, even though it maintains orthogonality to the legacy system, it induces ISI for itself. So its performance is not perfect in the sense that the SINR, signal to interference plus noise ratio, is less than the signal to noise ratio. However, in this design, SINR equals SNR, which means that no interference. So do you see the power of slowing down the transmission rate? So suddenly, after all, the excess bandwidth is same compared to the original legacy signal's transmission rate, just 22%. However, that 22%, when the transmission symbol rate of the overlay system slowed down, can be doubled as this one, quadrupled. And suddenly, it exceeds the Nyquist bandwidth required for zero ISI. So overlay signal can enjoy zero intersymbol interference. Of course, this theory by Nyquist under the definition of ISI, zero ISI criterion, is not information theoretical. Because as I told you, even if you have zero intersymbol interference, since you slowed down, you need information theoretic calculation whether this slowing down really benefits you in your design of the communication system in terms of mutual information between transmitter and receiver. The trouble is that in order to precisely speak what is required, you need to compute the mutual information between transmitter and receiver. And in this special case, it is possible if we assume that we utilize Gaussian symbol waveform. However, we don't know whether Gaussian codebook is optimal or not when we have unavoidable intersymbol interference. So the information theoretical discussion is not provided here. And you may find and you may have actually the result, what I talked about, by combining one of our papers in the reading list. And we will talk about that information theoretic result later. And as you may guess, if we assume, for example, not this kind of orthogonality condition, but just let's assume that our interference is Y-sense cyclostationary Gaussian random process. And we want to design our lag overlay system or our system with symbol rate exactly the same as cycle period or half of the cycle period, or twice the cycle period, 3 times, 4 times something. Actually, this slowing down does not help in that case. Slowing down does not help information theoretically. Then you may wonder why I provide this one. Because we can never design a system that is optimal information theoretically. Sometimes intersymbol interference is just regarded as an additive Gaussian noise. We do never try to exploit that something. Just we regard intersymbol interference as noise in many cases. In that case, having no intersymbol interference is better because we have better SNR. And what do? We may increase our modulation order of the data symbol. By doing that, high SNR, bigger size constellation may give us faster transmission rate. Got it? So as you see, every theory, even published in one of the most prestigious journals in communication society, has limitations. No paper is perfect because we are not living in a perfect world. And even if that paper is not perfect, we may still find some applications where that condition really matters. Got it? So always be humble, and also as a researcher, be proud of your result. Sometimes very theoretically interesting result, when you generate, you just regard it, it's just a paper to graduate as a PhD. It may be correct. However, if it advances the theory, especially theoretically, not just practically, in that case, anybody can advance that practical exercise. But if you improve some part theoretically, then it is worth to be published in prestigious journals. And at least at my old school academia, it was really appreciated, that kind of research. So one of the requirement in review, paper review, was this one. It was stated, is this paper has a permanent, has a worth, value as a permanent record. Got it? And that permanent record comes from the novelty of the paper and the amount of theoretical advancement. So anyway, at that time, especially in my early career, I pursued that direction. That's why I did this highly mathematical, even though mathematics world, it is not mathematical, it's just the applied mathematics. But anyway, highly theoretical result I generated, which has interesting observations like this. Your access bandwidth never close to Nyquist minimum bandwidth requirement can be doubled, multiplied, and somehow suddenly you can enjoy that small positive access bandwidth as your entire Nyquist bandwidth so that you have zero ISI, not only for yourself, but also in these cases, zero interference to legacy system. Got it? Anyway, so it seems that I talked too much as a preview, and let's see some mathematical part, because anyway, up to this paper, the first take-home exam, or you may say quiz, will cover. Got it? So some part of the problem will ask you to derive the result, which does not appear directly in the papers we have reviewed. Some result, you can just find out the location and just copy. And some question will ask you simplified version of the problem or some derivation stated in the papers. Got it? That's why I'm kind of doing a lot of overviews, because I wanted to include this paper in the coverage of the first take-home exam. Okay. Anyway, what should I do? Okay. Yeah, there are too much to talk about. Okay. Okay. So I will give you a simplified trick, which is utilized here. Suppose this is very simplified one. Suppose you want to design some vector S. Okay, that is complex 3-dimension of complex 3-dimension. So it's 3x1 vector you want to design. And of course, your objective is, for example, to maximize this quadratic form subject to the power constraint or norm constraint, and also orthogonality condition. So since most of you have taken the convex optimization or introductory optimization courses, you know mathematically how to approach this problem, right? This is what? This is a quadratic maximization problem with two equality constraints. And you usually, blindly speaking, you introduce two Lagrange multipliers. right? And you define Lagrangian and apply partial derivative with respect to two Lagrange multipliers. And then we know that if optimal solution exists, that pair of that optimal solution substituted in that partial derivatives, then the equality must hold. I'm not going to say that one. Here goes interesting trick. So whenever you have this kind of condition, actually, especially this one, what does that mean? You can not have some non-zero element in the first element of S, right? Am I right? Yes. Right? So E1 is 1, 0, 0. And your inner product, that should be 0, means this is 0. S vector has 0 element. Now, the trick is that you modify that one and remove this orthogonality condition, this equality condition. How you do that? So what we are going to do is that we are going to remove this condition so that we have only power constraint. And we modify this R into R tilde, but have the same problem. What do we do? That is the idea. So as you see here, this is exactly the more complicated version of that simplified one. So you have quadratic maximization with some equality, orthogonality condition, and power constraint. This is norm square of S, right? And you may say that it looks different from that one. Of course, that is simplified one with a single orthogonality condition. This one, depending on the size of B matrix, number of rows, number of columns of B, capital B of F matrix, actually you have how many? That number of column, many orthogonality condition. Got it? So here, you may rewrite it as E sub 1 Hermitian S, and this serves as B matrix here. Got it? And if you have, for example, B1 Hermitian S equals 0, B2 Hermitian S equals 0, then this can be combined as B Hermitian S equals 0, where B equals B1, B2. Am I right? As you learned in linear algebra, matrix algebra, right? Capital B Hermitian S equals 0, where B equals B1, B2, then this is same as two scalar equalities. This is vector equality. Sorry, this must be 0 underscore 2 by 1, right? So compactly written condition is same as this two scalar equality equals to scalar 0 equals to scalar 0. This is equals to 2 by 1 vector 0. Got it? So this subproblem is the key. And what do we do is that we introduce the orthogonal projection matrix. We introduce orthogonal projection. What is orthogonal projection, by the way? Suppose you have two-dimensional vectors, and you have a vector A and vector B1 and vector B2. And you want to find out the component of A vector that is parallel to the subspace spanned by B1 and B2, or orthogonal to the space spanned by B1 and B2. If you find the orthogonal component, then actually you are finding orthogonal projection matrix. Then how can you find? The idea is exactly this one. So what you do is that your matrix, if I remember correctly, this is the projection matrix to the subspace spanned by B1 and B2. And this is the orthogonal projection matrix. And here, as you see, by the way, this could be non-invertible. In that case, we need to use Moore-Penrose pseudo-inverse. But let me just say inverse. So this is P, B. This is P, B, perp, means perpendicular. Got it? And how do we modify? We multiply orthogonal projection matrices in front of this matrix C and after matrix C to obtain C tilde. Got it? In that case, the signal is already projected to the orthogonal subspace to subspace spanned by B vectors, so that our optimization will not spend any energy on that direction of B vectors. That is the idea. Okay, that's all for today.